can
one more,
find
like
our way.
one more thing, add previous to, previous to, yeah.
That's like the only thing. So that's what, this is what we're
Sums up.
Oh, papers. Yes, Chris.
I'm kind of signature.
I'm trouble with the references.
Yeah.
You got a minute after class? We're gonna go, I'll probably go to the lab. Let's work that out.
Please don't put this on the previous video.
Was it upsetting?
It wasn't upsetting.
It was upsetting to me.
Well, yeah, of course it was upsetting, but that's not the reason why I recommend not doing that. There's not enough math concepts in there to really get out of it.
You should have talked to me. There's math not there in there. Well,
I vaguely mentioned this, but it's not really cinematic money, so I'm not going to really talk about it.
that's what you can do, by the way, is you can always say, well, here's some of the math that this historical figure did. And they didn't mention it. And they should have. Just talk like that.
Mine was, we used Euler's method. I'm not going to tell you what it is, but we used it.
Euler.
That's a classic.
Close.
Who's got questions about the homework? Okay. So what homework questions do you want to look at?
Yeah, I focus a lot on
4 on 6.3.
Actually, I had everything done last week. And then I said, oh, I skipped my report. I need to go back to it. Then I went to go back, so I was like, oh, that's why I skipped it.
Exactly.
You could never
So
try
there's
that.
three problems in each of the sections, really cakewalks.
Straightforward.
Yeah, I can't even really see how
How'd you calculate all the Fibonacci numbers? It's right there.
I used Google and I got a big list of what to look from. Went up to like 15 and I just made the last couple I needed.
So from the formula that, wow, is this really true? Fn plus 1 times Fn minus 1 minus Fn squared is equal to either plus 1 or minus 1.
They said,
It works for the cases I tried.
So you try some cases. That's important. I would try that too. Let me write down a bunch of Fibonacci numbers and see if we can
Yeah, I just use algebra.
do this in front of you guys. We'll verify that. Wait,
I just
let's do that.
It feels like 4 should be in
It
there.
feels like 2, 3, 5, 8, 13. Okay, one more. 20 plus. Right?
Only going that far? The homework assignment made us go all the way up to 20.
Well, since you've already gone to 20, there's no point in me taking it any farther, although I'd be happy to.
I don't know.
Okay, so let's call this one the n plus first number at this point, and then 2 back would be the n minus 1, and then 13 there is the middle one, the nth one. So what this is saying is that 8 times 21 minus 13 squared is equal to plus or minus 1. And that number is, let me think, 168, and that number is 169. So in fact, it's not plus or minus 1, we got it better, it's minus 1. And furthermore, this is supposed to be, this is the real question, do we have the indexing right? Is this really minus 1 to the n power? So n should be an odd number. If you raise minus 1 to an odd power, you should get a negative 1. So is n an odd number right here? And the number, the Fibonacci number is 13. That's not what I'm asking. It's n, what position we're in. And also.
7, so yes.
So where do you start counting? Do you start counting at 0?
I tried that, but it made all the numbers not work.
Aha. So this is using the old school convention that this is the first one. Because it goes 1, 2, 3, 4, 5, 6, 7. We needed it to be ordered out number. The modern convention is you start with 0. And then this formula has to be adjusted. How would you change the, so when we write it as fn minus 1 times fn plus 1 minus fn squared. In modern notation, the thing on the other side is not the nth power, it's the n plus first power, or n minus 1. So it depends on how you start the indexing, right? It depends on whether you call the first one 0 or the first one 1. But yeah, that's fine. Let's leave it with the old school interpretation. So these numbers begin with the first Fibonacci is 1, the second one is 1 also. And then we're supposed to use that to conclude that the numbers are relatively prime. So did everybody know what relatively prime means? That's right. If they have no common factors. So if they had, if you find a number that's a common factor, it's just 1. So there's no non-trivial number that divides both numbers. In other words, I like GCD as well. Does everybody know how to compute the GCD of two numbers?
Yeah, you plug into that complicated formula you put on the exam.
Yeah, right. We'll put it into Euclid's algorithm, Euclidean algorithm. And we can compute the GCD. All right. So what are we trying to do here? Consecutive Fibonacci numbers should be relatively prime from this. Let's talk about maybe the nth one and the n plus first one. And since the product of n plus 1 times f minus 1 and f sub n squared, those differ by 1. Let me ask this as a question. Could this product and f sub n squared have any common factors? I'm just realizing I'm completely off screen for that movie camera. Let me re-ask this question over here. Maybe with a darker marker. So we have the two parts of that formula, right? Fn minus 1 times Fn plus 1 and the square of Fn. Numbers that differ by 1, or either one's bigger, either in one order or in the other order, you get 1 when you subtract. Can they have a common factor?
Yes.
Well, what would it be?
1.
Okay, fine. But that's it, right? If they have anything in common, it's a 1. Why is that? Let me argue by contradiction. Suppose they did have a common factor, d. Then these two quantities, since they both are divisible by d, are either equal or they're d units apart. So the answer is no, because if they had a common factor, what we're saying there is both of them would be a multiple of d, of this divisor, this number that divides both of them. A quick way to say it is this: they must differ by a multiple of d. And that's an immediate contradiction because they differ by 1. So if these two things had no common factors, is it possible that f sub n minus 1 and f sub n have a common factor? Those are the consecutive guys. No way, right? Because why? Well, if there was a common factor in there at all, it's possible that it could, you'd find that it would, that d went into this one, and of course d would have to go into that one. That d squared would have to go into this one, but we know there isn't. Same argument. So those things differing by 1 gets you that not only do they not share any factors, but all of their subfactors can't possibly share factors. I'm trying to think about how to formally say that last bit. It might be another proof by contradiction. Suppose you did have a common divisor of fn minus 1 and fn. That's a good way to go. If there was such a common divisor, then it would be a divisor of this product and of that square. Right? Well, that would contradict the fact that we just saw they can't have a common divisor. Oh, that's cool. So that's, what's in 250 again? Did that feel like a good exercise to you? I think I was suggesting that one to your 250 point.
I believe so.
No? No?
That's all right. You don't have to do that.
Because he's always looking for good problems.
Have you guys even done proof by
Have you done the
contradiction?
proof by contradiction part then?
Yeah.
That's news to me that we have done that. So
Say again?
I said it's news to me that we have done. So that's shows where I'm at.
We did last class. I think so.
It all blends together today.
Proof by contradiction is in many ways the sharpest razor in your toolkit. But it's a weird, can I just make a spiel about proof by contradiction? Sure. You have to get used to this zen of that mode of thinking where you intentionally put yourself into a world where the thing you're trying to prove isn't true. So you intentionally say, well, suppose they did have common factors, and then reason from that position. That is weird because you know this isn't the case. You have to pretend that it is, and then reason from there until you achieve something that's ridiculous. That's not the direction your minds have been trained to go, right? You usually start with stuff you know is true, and you try to reach reasonable conclusions that will help you get through the world. On purpose, try to achieve something that's nuts. It feels very strange. And so you have to get used to that phenomenon. It's extremely powerful though. Right? When you show that the assumption that your statement is not true leads to the ridiculous, you were wrong about that initial assumption. So the original that must have been true. That's really my favorite way of arguing.
If it's so powerful like that, why is there a bunch of mathematicians who are adamantly opposed against using that kind of proof?
I wouldn't say there's a bunch.
There's like 5 people.
There's a small category of people who not reject it, but would say, if you can find a direct argument, then that would be better. I think that's what most of people's attitude that are against it. They're constructivists, they're called. And they would say, a forward direction type argument that works from axioms to get to a final conclusion is preferable. So if you can do that rather than the proof by contradiction, do it. But I think that's a pretty small group. These constructivists are the vast majority of mathematicians care about just getting the stuff proved and moving on to the next thing. And sometimes the proof by contradiction stuff is really pretty. I mean, it just comes out to be you get to the end of the proof and you go, wow, mind blown. I'm in awe, right? How succinct the argument becomes when you finally see the right round. So yes, that was number 4. What did you have one too? There's nothing on that one on the quiz, if that's right.
Number 5.
5 from the same section? 2. Wow, did I really ask you to do this? It was so hard. Assuming that x and y are integers, find a number of the form 4 times xy times x plus y times x minus y that is divisible by 5. The quotient, what quotient? Being a square. Quotient? You have to have two numbers to talk about a quotient.
Yeah.
Oh, I see. That is, if you divide it by
It
5.
was written funny.
If you divide it by 5, you'll have a square. I got it now. So how about if x and y were 1? Would that work? We have 4 times 2 times, oh shit, 0.
Yeah.
Okay, so I don't want x and y to be equal. All right, how about if x is 2 and y is 1? Then I have 8, 3, and 1. No good yet. I mean, I'm thinking we just play like this, right? But I have decided that, hey, wait a minute. I know how to get x. I know how to get something that's got a 5 in there. Well, you could put 5 in it, but there's a quicker way. This is the biggest number involved, right? If you make x and y add up to 5, it'll work. You'll have a 5 written right there. I was being stupid about that. Yeah, how about 2 and 3? Right? Yeah, that'll work. So, okay, so this is 5.2.
I was lazy and just said, let x be 5. No.
X equals 2, y equals... No, wait, let's do it the other way so that
Yeah.
the difference doesn't come out negative. Then we get 4 times 3 times 2 times 5 times 1. So, by the way, if we divide by 5, I just did it. Right, it just rolls off the 5. I'm so proud. And what's left? A square. Okay, so we want to make x plus y add up to a multiple of 5, and then we want 4xy times x minus y to be a square. Another inch.
4?
Oh, wow. I don't know. Let's see. 4 and 1. We could try it. X equals 4, y equals 1. We have 4 times 1. Looking good so far. And then we have our 5. But no, then we're going to get the 3 from this. From the x minus y part. That was so close. We got a square, and then that 3 must have known. Yep.
Can we do 5 and
5 and numbers?
2? 2? Would that work?
5 and 2 adds up. Oh, wait a minute. Are you thinking about we get the difference somewhere else?
I was thinking of like, yeah, using the like factors.
Using x or y being 5. That's another approach to this. Okay, does that work? Does that?
I hope so. What?
Well, I mean, in a way, I always hope not, because we keep exploring. We'll find the right thing.
Yeah, we keep exploring, and we won't have time to do quiz. I hope I'm wrong too.
So x is 5, y is 2, is your suggestion. So then we have 4 times 5 times 2 times the difference is, I mean the sum is 7 and the difference is 3. I mean, take away the 5, I don't think that's a square.
No.
No. Wow. Yeah.
I
So
just,
Vasana probably got it, right?
so this might,
But,
I want to give you my line of thought.
okay, let's
See
hear
if
your
that
mind.
helps. So I set x equal to 5, and then I divided it out, and you're left with 4y, parentheses 5 plus y, parentheses 5 minus y.
So wait, you're
equals n
actually,
squared.
you're assuming x equals 5, just making that substitution in the thing.
Yes.
You're saying the formula is 5 times y times
We lost 4 now. 4 times.
4 times y, because we're going to divide
I
out the
divided
5,
that by
right?
5. If you want to show it
Times
and then divide it, that's
5
fine.
plus y times 5 minus y.
y equals, I used n squared, because you want it to be a square number. And then I said the easiest way from there is to make each of the separate terms be a square number.
You know what I just realized? The way I like to work with polynomials, I've probably written these the wrong way. Let's assume y is the bigger number, so that I can write this stuff here as y plus 5 times y minus 5. So, yeah, 4 times y plus 5 times y minus 5 is equal to, let's just say 4 times y times that sum and difference of the same thing gives us y squared minus 25, right? Because the outer terms and inner terms cancel. And so finally we get 4 times y cubed minus 25y over you could kind of leave the 4 out of it all, by the way, because if this part is a square, 4 times it will also be a square. So what I would probably do next is just have a look at that formula on the calculator.
Okay.
I mean, we're not in ancient Greece anymore, but we can treat it a little bit. Is that ever going to be equal to a square?
I have a funny feeling it will be.
Why is it funny?
I'll explain it a little bit.
Oh, yes. Yeah. So put in your y equals, we want y cubed minus 25y. Well, okay, I don't have a y button, so it's going to be x cubed minus 25x. Now we look at the table here. Why is my table starting up like that?
This is the last time you started.
Maybe that was equals. Well, 0 is a square. Right? I can definitely use that. Maybe I'm not liking that as a square. Do you recognize squares that are this big, though?
No, but I saw 36 times.
You saw 36. No, just moved over. You saw 36. Oh, you saw a negative 36. Negative 36 is not a square. If we could fix that. Is that how you found it? You used the negative value there?
We didn't switch the y plus 5 to y minus.
Here's my, oh, I see, you looked like that. So here's a good trick to do this thing. I'm going to insert the square root thing here. What will happen to the square root of most of those numbers? Well, the negative ones, it'll say error now, right? See those errors? And then we get things that usually have decimal places. The one that doesn't. There's one that came down to a 10th. Look, there it is.
Oh, that's the problem with the formula. When he went from 5 minus y, he went to y minus 5. The negative sign should have stuck with the y, not the 5. That's why we're getting variance.
Oh, I see. This is the negative of what.
Yeah. So the 36.
So what I was doing was just making the presumption that y was the larger number, rather than thinking about preserving the original formula. All right. So in effect, switching the roles of x and y.
Sorry, definitely.
But still, we've got a value for y now. That's 24. Let's see if this really works. So x is 5, y is 24. Oh, that's not a good word. Just tell us the kind that we'll never erase. X is 5, y is 24, so we have 4 times 5 times 24 times the sum, which would be 29, times the difference, which would be 19. Now, why is this a square? Even after we divide that out.
You went off in a different direction.
I went up in a different
So-
direction than you did, okay.
So why don't we do it like this? Is there a number that we can substitute in for y so that, you know, y plus 5 is a perfect square? That also happens to be that 5 minus y is also a perfect square. And the number jumps out at me, and the perfect squares being 9 and 1, or 1 is square.
If you want two perfect squares that differ by 10,
By 8.
represent y minus 5 and y plus 5.
No, it's 5 minus 1. If you assume that y is the smaller number, then you get nicer numbers.
Sure, you can try it your way. So we're assuming y is smaller than 5.
Yes.
What assumption, what value of y are you finding in 5? Y is 4. And x is 5.
And x is 5.
That one.
Yes. Because then when you divide by 5, on the outside you have 4 times 4, which is a perfect square. Then you have 5 plus 4, which is 9, also a perfect square.
So you're saying, let's just look at your answer. We've got a 4 from the formula. There's a 5 from x, which we're going to cross off. There's a 4 from y.
Yep.
Then there's the sum,
5 plus 4.
9,
Yep.
and their difference,
5 minus 4.
1. Oh crap, that really doesn't, does it? So what was the thinking here? You wanted
I wanted everything to be a perfect square.
x is 5, so it's the thing that we're going to cross off in this thing. And then you wanted the sum to be a square and the difference to be a square. And this is 5 minus 1. Smaller square. Yeah, that definitely does the trick, because if you're thinking about 5 minus y being a square, there aren't many squares smaller than 5. This would either have to be, y would have to be 4, to make that a 1 by 1 square, or I guess if y was 1, can we do it for y equals 1 too? Oh no, because 6 is not a square. But there's many fewer things to check then. Like that. I'm still not clear why my 115 didn't work. Because I found the part that doesn't. I found this part being a square. Is it possible that number isn't actually a perfect square? Oh, crap. Look what it did to me.
Why would it do that?
Look what it did to me. That's what the problem is. That number is not in fact a perfect square. It's just been rounded to a perfect square. With a rounding error. Now, see, I was really hurt here. So wait a minute. Is it possible there aren't any actual round, whole numbers in this size?
Certainly seems.
Gets really close, but it doesn't equal it. Oh, there was one. No, not really. Got 0.99 something in it. Oh, 300. So wait, this. See, if I was a smarter calculator operator, I would have come down to 45.
Let's give that a try.
Yes, can we? Because I was like, I know this approach works. All right, so y is 45. Let me just make the change like that. X is 5. So it's 4 times 5 times 45 times 50. That's the sum, times the difference of 40. And that 45 times 40 times 50 times 4 is a square, according to what we just worked out. Is it a square? Well, by calculator we can certainly figure this out, but let me do it by hand. We've got, this guy is 2 squared. This one is 5 times 3 squared. This is 5 times 2 times, well, 5 squared times 2, right? And this one is 4 times 10, so 8. I was trying to write these with powers. 2 cubed times 5. Oh, there's nothing but 2's and 5's in that factorization, which is good. What's the exponent on 2, all told? 2 there, another 1 there, and 3 there, so 6. The next power is 3, or the next prime is 3, and that's appearing just to the second power. And then the 5's, we have 1, 2, 3, 4. From prime factorization, you can notice squares because they just have even exponents. All the exponents are even. So this is the square of 2 cubed times 3 times 5 squared. So I like your answer better.
Well, now we know a different way to do it.
This one seems more extendable if we can't immediately see, you know, the number that just happened to work this example.
Yeah, but you know what happens? What we've got there is a Diophantine problem. We're looking for an integer solution to a cubic polynomial being a square. So it's a solution of x squared equals this cubic polynomial. There might not be any solutions. There might not be integer solutions to that. And a big part of Diophantine analysis is to figure out what conditions tell you that there can't be solutions. And you know, I didn't check the discriminant of this. This is what's called an elliptic curve. When you have wait. Yeah, because it's messed up. It's x squared equals a cubic in y. Normally it's y squared equals a cubic in x, but it's still an elliptic curve, just with the roles of the variables switched. Elliptic curves may or may not have whole number solutions on them, and it depends on pretty advanced algebra. Yeah, so the abstract algebra people, who's an abstract? An elliptic curve, when it does have rational points on it, points whose coordinates are rational numbers, forms a group. Points of a variety like that can be just treated as group elements, and there's a group operation.
Now do the part B.
Okay. Oh, there's B.
Before we get part B, a question for you.
Yes.
That thing you were talking about earlier about determining whether or not any answer could possibly exist. When did we learn how to do that?
Grad school.
Grad school. Thank you.
Prove that if x plus y is even, then the product, that's everything except for the 4, right? We've got, the formula was 4 times x times y times x plus y. So if x plus y is even, then the product, x times y times their sum times their difference is divisible by 24. And that without this restriction, without this restriction, because the restriction being that x plus y is even, the whole thing is divisible by 24. Okay, they've given us a hint. So any number can be written as either a multiple of 3, or 1 bigger than a multiple of 3, or 2 bigger than a multiple of 3. Well, why not 3 bigger than a multiple of 3? Very nice. That's another multiple of 3. So you're sort of back in this case, if you just with a different k. Okay, so we want to show that 3 divides this thing. Why is it enough to show that 3 divides that thing? Because I'm looking at the number 24. And that means I need to show that 2 divides it a bunch of times. 2 divides it, well actually 8 divides it. So 2 cubed needs to divide that product. is even, I know that x minus y is also even. Not everybody knows that. Front row is shaking their head. So let me argue this one for you. Suppose x plus y was even, and x minus y was odd. I'm going to use contradiction again if you can't tell. If x plus y was even and x minus y was odd, what do you mean? How much do those differ by? Notice that x plus y and x minus y differ by twice y. Right? So that's an even number, right? If y is a whole number, 2y is even. So they differ by an even number. So if this one's even, and you take away an even number from it, what are you going to have? Let me put it another way. If x plus y is even and x minus y isn't, what's their difference? You have an even number minus an odd number? It's got to be odd. So we know for sure they differ by an even number, and if one's even and the other's odd, they differ by an odd number. That's a contradiction again. Becoming my favorite symbol, the arrowhead's budding. It says, nope, that can't be. So you know that, in fact, we don't have one even and one odd. They have to both be. We're both odd. They could both be odd, right? And that is the scenario that's bothering me right here. If x and y are both odd, then I have odd stuff in there. I'll have an even number here, x plus y, and an even number there, x minus y. That's giving me 2 powers of 2, or an exponent on 2, that's equal to 2. It's giving me 1, 2 from the one and 1, 2 from the other. Turns out no. It's actually getting me, one of those is going to be what's known as doubly even. I don't know. It is, but it's got 2 2's in it rather than just a single 2. So we're going to have to argue that. Well, anyway, let's get on to this part. Consider that any integer is of the form 3k, 3k plus 1, or 3k plus 2, and showing that 3 has to divide this stuff. Well, yeah, okay. Say the argument is a hint on the other part that 8 has to divide it. We're going to come back to that. Let's look at how this is about what's really mod 3. Not everybody's heard of mod 3, but that's I know mod. Okay, so you work mod 12 all the time when you do time when you work on the clock, because if it's like 11 o'clock now, what time is it going to be in 3 hours? Yeah. So you just told me that 11 plus 3 is 2. Leave the rest up. But what we're doing is we do this adding, and then we say, yeah, but we've gone around the clock once, so we mod out by that. That's what it's called, mod out by 12. And so you get 11 plus 3 really can be equal to 2. It's just the clock arithmetic, or modular arithmetic. Here we're doing this notation of 3k, or 3k plus 1, or 3k plus 2. That's mod 3. So it'd be a weird clock that had 3 hours on it. You know, you'd have at the top, you know, and clocks are ancient. They come from Babylon. They have 12 at the top. If mathematicians were designing these now, they'd have 0 at the top. In fact, don't they call it 0-100 hours in the military? Right? So that's, huh? 2400 or 0-100?
No, it's 0.
Yeah. 1200 is noon. But then it's 13. Say they work mod 24. They got 24 hours on their clock. But anyway, if you had a clock that had these just 3 marks on it, like that, they would probably, in modern times anyway, they'd be labeled 0, 1, and 2. And that's what you're seeing here. Multiples of 3, going just around the clock some number of times if you're stopping at midnight, or a multiple of 3 plus 1, we go around and around and around and around and go 1 more. Or multiples of 3 plus 2, where you make your final stopping point here after some number of times around the clock. The 3K is just is what I'm saying, K times around the clock, and then how much action. But every number falls into one of those 3 slots. Another way to say this, by the way, is think about division. If you divide a number by 3, what possibilities are there for remainders? 0, 1, or 2, right? You can't have any remainders bigger than that because, well, you're dividing by 3, and the remainder is always smaller than the divided. So, yeah, these numbers 0, 1, and 2 are also the remainders that are potentially calculated divided by 3. Okay, so cool. We're going to say that any number is one of those forms. What are all the possibilities for x and y if we want to look at 3k, 3k plus 1, or 3k plus 2 for each of them? Maybe I should say x is in this list. It's 3k, 3k plus 1, or 3k plus 2. And I think we want y to be in a different list because I don't want to assume that x and y have the same k that goes with them. So I'm gonna use a different letter. Unfortunately, L's look a little weak when you go to write them on the board. They get confused with ones. So watch my typography. I'm gonna make these curly L's. So those are the possibilities. That means 3 for x, 3 for y. We've got 9 different potential things to work about. But we can get it's easier than that. It is. Why is it easier than that? If either one of them was 3k, or the other one was, if either was a multiple of 3, we'd already be done. Right? We know that 3 divides even. That's simple. I hope. Actually, some of you will not have known that simple. What this vertical bar here is saying is not divide. A lot of times people think it's do the division, but it doesn't mean that. It means ask yourself the question, if I divide it, would it come out even? Would there be a remainder? So you read that vertical bar is 3 divides evenly into that chunk. So yeah, let's see if we can do this now. If either x or y look like a multiple of 3, we're already finished because you got your 3 sitting there in either x or y. So if these things happen, we're done. We can stop early. Right? So then that means we can ignore those cases. Right? So in fact, there's only 2 potential things for each. Right? Okay, so we've got this is the other approach. I usually dislike this approach, but here it's seeming like the way to go. If you've got 4 potential cases that your problem can fall into, just look at them all. There's four things to observe, and hopefully in each one of them we'll see that 3 divides the numbers we're after. That's usually regarded, by the way, as one of the less aesthetic ways to proceed in a proof. You know, ideally you get to the end of a proof by cases, and then you figure out what's really going on, and you can write a direct proof or something else. So, but let me do the cases here. Case 1 would be x is 3k plus 1, and y is 3l plus 1. So x times y times x plus y times x minus y looks like 3k plus 1, okay, not divisible by 3. 3l plus 1, also not divisible by 3. Ooh, what do we got here? When we add up x and y, we'll get 3 times k plus l. and then plus 2. Not a multiple of 3. But what about when we do the difference between these two forms?
Good feeling about it.
Yeah, that one is 3. Well, the 1 and the 1 are going to cancel each other, right? So we have 3k minus 3l. It's 3 times k minus l. So this guy, right? You just point at it and say divisible by 3. There's a 3 that you can factor out of this whole product by pulling it out of that. So what's the remaining cases? Well, we've got, suppose we had 3k plus 1 and the other possibility for y. L plus 2. So I'm going to write the factor form of our thing. It's 3k plus 1, and we'll go for that. 3l plus 2, that's not helping either. Neither of these are multiples of 3. 3 times, well, what do we get when we add them up? 3k plus 3l plus 3.
Let's factor out the 3.
That's got a 3 in it. You see the 3 that's sitting in that? Every term has a 3 in it, so that's divisible by 3. And then the last thing would be 3 times k plus l minus 1. Well, anyway, not divisible by 3. But this guy is. So I guess maybe I'll say you should try to do the rest of them. Right. But I'm starting to get to that point I was saying where, you know, after you do the cases, oh, maybe we should just lay out what are the remaining cases. We dealt with everything that has x is equal to 3k plus 1, because y was the other two choices. First the first one, then the second one. So we're done with that. Now we need to do the 3k plus 2, and this one, and then 3k plus 2 from that. So case 3, x is 3k plus 2, y is 3l plus 1.
You really need to do case 3.
And case 4, actually, I would say you don't need many of these cases after you see what's really going on. Right? And so what is really going on? Let me just point at it for you. If we're in the first case, the difference is divisible by 3. We'll see it. Right? Because the ones will get killed off when you do the subtraction. If we're in the second case, it's the sum. So as x and y range through these possibilities, just figure out which is going to be divisible by 3, the difference of the sum. It's never going to be x or y. But these guys have a sum that's divisible by 3. What about those two when it's the difference? The 2's will get canceled off when you... So if they are in the same category mod 3, if they're both 1 mod 3 or they're both 2 mod 3, the difference will do it. And if they're in different categories mod 3, then the sum will be divisible by 3. There's an argument to, you'd state that pretty nicely. Lastly, we've got to show that not just 4 divides it, which we could show by all elementary means, but that 8 divides it. So any integer can be written as 8k, 8k plus 1, ... all the way up to 8k plus 7. What's the clock look like if you're thinking about multiples of 8? Realize I didn't finish writing down that fourth case, but those are the ones that you should fill in if you want to follow through the cases already. Yeah, clock arithmetic with the date numbers on it. That's 0, well, like that. Yeah, that wouldn't have been an unreasonable way to lay out the clocks in Babylon. I'm surprised they didn't decide to use just 8 numbers, because it's easier to find the positions.
And you can divide by 3. Divide by 3 is super important.
Oh, but they had to construct, what are those angles, 36 degrees or something? 360 divided by 12, 30 degrees. Only 15. I cannot figure this out in my head. What's the angle between 12 and 1? 3 of those go into a 90 degree angle. That's 30 degrees. Woo! Yeah.
60 divided by 12. It's just.
Yeah, I know. I just, for some reason, I was looking at that going, that is not a 30 degree angle, but at least it is. Sorry. So, X, I don't think that we're going to get 8 dividing X times Y. I'm thinking we have to look at X plus Y times X minus Y. So we're going to look at things that look like 8K plus A. X is 8K plus A, and Y is 8L plus B. And then, if A and B are equal, what does it look like when we do the subtraction of X and Y? So let me write it in a more succinct notation. If A equals B, then 8 divides X minus Y. There's a notion of being a negative of a number in clock arithmetic, and that makes some sense here too. Can you see what's like, for instance, if I look at 3, what's the negative of 3? Okay, Mike, you're on to it. So what are you asking yourself to come up with the negative of a number? It's, well, one way to think of it is, instead of going around from 0 that much, go back from 0 that much. So that's the negative. The negative of 3 would be 5. Another way to say it, though, is, what's the negative of a number supposed to be? It's the thing that if you add it together, you get 0. So to say, what's the negative of 3 is to ask this question. What other number could I add to 3 and get 12? I mean, 0. I mean, yeah, the top of the clock. You see that 3 plus 5 will get us up to the top of the clock? What's the negative of 2 then? 6. 2 and 6 gets you to 0, to 8. Negative of 1? So look, I can pair up the negatives this way. Oh, 4 is its own negative. You ever run into that in ordinary math? A number that's its own negative? Well, 0 does that, doesn't it? Plus or minus 0, that's one number. Okay, so if A is equal to the negative of B, then 8 is going to divide their sum, because that's what that means. If a number plus its negative is going to get you to the top of the clock again. So we're done in those cases. What we need to do is figure out what happens when X maybe is here and Y is not there, and also not here. So it's any one of these other positions. We don't want to use 0, so none of them should be of the form 8K plus 0, because then the X and the Y, and where the Y could have it. So we don't want to have 0 as one of our possibilities. Anyway, I'm going to chill out here. The rest of this is about figuring out what other cases there are. Either they're equal, or they're negatives, or what remains. And we're out of this. Yeah, we're going to do the quiz next class.
Yeah,